Hey everyone, welcome back to Cosmobites. Today we've got 10 minutes of the absolute best Brian Cox clips, all about the wonders of the universe. Before we blast off, make sure to smash that like button and hit subscribe so you don't miss any cosmic adventures. All right, let's dive in.
It is possible that the universe is eternal. There's a lot of debate about it, actually, because Stephen Hawking and Hartle had a theorem that said that any universe that always expands has a beginning in time. But there are people that try that you can sort of get away. So that's cutting edge cosmology. I don't know what it would mean if it turned out that our measurements suggested that the universe is actually eternal, and it's only our bit of it that had a beginning in this Big Bang 13.8 billion years ago, but there was something before that, we think. How long that existed for, we don't know. Did the framework exist forever? Is it logically necessary? Does it need to be laid down? That's cutting edge. So I honestly don't know.
There are stars that are literally the size of solar systems. So the more massive the star is, a star, let's say 10,000 times the mass of the sun, then it has to burn its fuel extremely quickly to stay up against the force of gravity. So they're very, very, very short-lived, the really massive stars in the universe. I don't know the figure for the biggest star, but one of the biggest you can see with the naked eye, actually, is Betelgeuse, or Betelgeuse in Orion. And what's interesting about that is if you put it where the Earth is, then it would extend out pretty much to the orbit of Jupiter, I think even beyond the orbit of Jupiter. So if you imagine how far it is to Jupiter, that would be orbiting inside the star. And it's so big that we can see sunspots on the surface with telescopes here on Earth. So it's a vast star. That's a star at the end of its life that's swollen up. That isn't, however, the biggest.
As Jupiter is made of gas, could you fly a rocket straight through?
No. So you could fly a rocket through the upper bits of its atmosphere, where it's not quite as dense. But if you go down towards the core of Jupiter, the pressure becomes so high and the temperatures become very high. We think there are all sorts of exotic materials. We don't really know what's at the centre of Jupiter. We have a spacecraft called Juno at the moment, which is orbiting around Jupiter to answer that very question, trying to work out what is actually in the middle. We think that exotic things called metallic, liquid hydrogen and all sorts of really strange materials. But if you tried to fly a rocket through the centre, it wouldn't get very far. It'd get squashed and crushed and melted. And then it may well hit something very solid indeed in the core. We can look so far out into space that we can see the light from just after the Big Bang, about 380,000 years after the Big Bang, actually. And in that light, before there were stars and galaxies, there are also patterns that match on to the way the galaxies are distributed in the sky today. And where did those patterns come from? Well, the best theory we have is a theory called inflation, which says that before Big Bang, in the sense that before the universe was very hot and very dense, it was still there and it was kind of cold and empty, but expanding very fast. And then that very fast stretch of the universe came to an end, slowed down, and in the slowing down, the universe got heated up and all the particles out of which the stars and galaxies are made were created. So that's called inflation. There's good evidence for that. Didn't have one once.
Do you think that one day we will use wormholes to time travel?
It's one of the big questions in theoretical physics, whether those things, first of all, can exist. They can, given Einstein's theory, but there's a question about whether they would be stable. So there's a question about whether, if you tried to send information through them, then they would collapse. And it's a big debate at the moment, actually. You use it as a time machine to go into the past. And I think most physicists think not. They think that whilst they could exist, they would be unstable and collapse again. And so you'd never be able to send information through, let alone a person. Even one little light signal wouldn't get through it into the past. But we need the more advanced theory, the quantum theory of gravity, to be sure.
Some planets like Earth and Jupiter have a magnetic field, and some planets like Mars and Venus don't.
So Mars is a small planet compared to the Earth. It means that its surface area is larger
in relation to its volume. You see this in the natural world, actually, in animals. So things like little mice and little bats and things have to work a lot harder to keep their body temperature. So all planets, when they form, you've got loads of rocks coalescing together. They come together, you get heat in the center. That's added to by radioactive decay in the center of the planets. So you've got a certain amount of heat in the core, and it's been radiated off into space. And the smaller the planet, the faster it radiates the heat through its surface, because its surface is bigger in relation to its volume. So you would expect a planet like Mars for its core to solidify. You've not got this nice iron core that can spin around anymore, the liquid iron core, molten iron core, and so you lose the magnetic field. Mars is the only planet we'll colonize beyond Earth, but it's an easy planet to colonize. It's got water in abundance below the surface, we're sure, or frozen in the ice caps. It's got all the minerals that we need to build a civilization. We have the technology to go and extract the water and turn the water into oxygen and hydrogen for us to breathe and to make rocket fuel and electricity, all the things we need to build a civilization. So we know how to do it. So it's just whether we want to or when we want to. Most of the plans I've seen to go to Mars involve setting up the base first with robots and then going to the base. So it's almost we build the base first and then we go and move in. And I think that's what we're going to do.
Do you think we need to terraform?
Terraforming is changing the atmosphere of the planet. And that's a longer term goal, but we know that we could do it in principle. There's a place called Hellas Basin on Mars, which is a big, almost certainly an impact crater, impact basin actually. It's 9 kilometers down to the floor. So that means that although it's so big you couldn't see it, if you put Everest in the middle, you could look down on the summit from the edge. It's so deep that the atmospheric pressure is so high at the floor of the crater that liquid water can occasionally exist at the floor. So already, although Mars's atmosphere is very thin, there are places that are so low in altitude that the pressure is high enough for liquid to exist momentarily there, even now. So you can see that the atmosphere of Mars doesn't need a lot. It needs things like greenhouse effects, carbon dioxide and things thrown into the atmosphere. But then you can imagine growing plants, and the plants would produce oxygen, and the water's there for them to do that. And so you could imagine at some point in the future that we end up with an atmosphere on Mars again, because it did have one once. We can look so far out into space that we can see the light from just after the Big Bang, about 380,000 years after the Big Bang actually. And in that light, before there were stars and galaxies, there are also patterns, which are patterns that match on to the way the galaxies are distributed in the sky today. And where did those patterns come from? Well, the best theory we have is a theory called inflation, which says that before the Big Bang, in the sense that before the universe was very hot and very dense, it was still there, and it was kind of cold and empty, but expanding very fast. And then that very fast stretch of the universe came to an end, slowed down, and in the slowing down, the universe got heated up and all the particles out of which the stars and galaxies are made were created. So that's called inflation. So there's good evidence for that. We need the more advanced theory, the quantum theory of gravity, to be sure.
How the moon was made?
It was made in an impact. So very early on in the life of the solar system, so let's say 4.5 billion years ago or so, we think that a planet about the size of Mars collided with the young Earth. It's sort of a glancing blow, actually, which caused a lot of rubble to go out into space, formed momentarily a ring around the Earth, somewhat like the rings around Saturn, but then that ring very quickly coalesced into the moon. So we think that the moon is made of mainly bits of the Earth and also bits of this other planet that glanced off it. Something like 4.5 billion years ago. It's very, very early, very soon after the Earth formed.
How can light be both a particle and a wave?
Experimentally, we find when they interact in particle physics, what do we see? We see essentially a game of billiards. Right? We see things with mass, or indeed with no mass, in the case of photons, little particles bouncing off each other. In order to describe where they're going to go, so you can ask the question, I've got a particle here, where's it going to be at some later time? Where are they going to go? The mathematics that describes where it's going to go is very wave-like, and so particles behave like waves in the sense that if you want to calculate where they're going to go, you end up with things you get with waves, properties of waves. The way they move is not like the sort of particles we can imagine. If you bang the two together, you go boing, and that one goes off. You can calculate it, but the maths you use is quite wavy. For example, with a wave, you can get what's called interference, which means that the peak of one wave lines up with the trough of the other one, and the waves cancel out. And you get that with the way that particles move around. The best thing to say, my prejudice that particles are particles, but the way they move is not like the sort of particles we can imagine. If you bang the two together, you go boing, and that one goes off. You can calculate it, but the maths you use is quite wavy and wave-like. So that's the way I look at it.